students, welcome back to Wisdom Academy YouTube channel. In the previous video, you have learnt about electric flux and Gauss law, where electric flux was the total number of electric lines of forces passing through a given area normal to it, and we learned Gauss law, which was the total flux is equal to 1 by epsilon naught time charge of the net times the net charge enclosed by a Gaussian surface. So, in today's video we will learn about the applications of Gauss law. So, Gauss law, why he gave that law is to simplify finding the electric fields. We know electric field formula is K into Q by R square, but what happens if I want to find the electric field for a uniformly long charged wire? So, I have infinitely long uniformly distributed charged wire. So, I have a wire which is very long and it is having charges over it. So, I can write plus or I can even write minus. There is no hard and fast rule for that. If I write minus, electric field will be towards it. If I am writing plus, electric field will be radially outwards. I hope you are understanding. This is the wire, and how the electric field will be in this direction, this direction, this direction, all the direction. It will be radially outwards. If I draw in here, it is something like this, spread in all the directions. I hope you are able to feel. Can you feel what I am trying to say? It will be spread in all the directions like this, right? So, I have a infinitely long charged wire and I need to find electric field at one point. Let the point is somewhere here. I want to find what is the electric field at this point due to the infinitely long charged wire. So, for finding that, what we need to do? We need to draw a Gaussian surface. So, first whenever you want to find the flux and you are using Gauss law, then you must have a Gaussian surface. So, to draw a Gaussian surface, I said it is an imaginary surface which is drawn in such a way that it encloses all the charge. So, here the best Gaussian surface can be a cylindrical Gaussian surface like this. So, I have drawn a Gaussian surface which is cylindrical. So, when it is cylindrical, it has one curved surface area and two circles are there. So, this is one area, this is another area, and the third area is the curved surface area. So, I will write it as suppose I am writing it as S1, this is S2 and this is S3. S1 is the curved surface area, S2 and S3 are the circles which are present on top and the bottom. This is the closed surface, Gaussian surface what I have drawn for this case. I just write the heading as this is the first application, and that is finding electric field of an infinitely long charged wire. So, when the charge is distributed linearly, I will have a concept of linear charge density here. I hope you remember what is that. Linear charge density was lambda, that was equal to Q by L. Lambda was charge per unit length. So, now what we will do? We will try to find the electric field. For that, what we should do? We have drawn the Gaussian surface, and the Gaussian surface, the flux will be coming out like this, isn't it? Will the flux go in this direction? Definitely not. It will come only in this direction. But this particular S2 and S3 surface, they are normal vector. I said you, whenever you want to use the concept of flux, flux used to be E A cos theta. There you must make sure that this A is the normal component. So, this A, this is the area direction, n cap, and in this case this is the electric field, this is the n cap, isn't it? So, these two surfaces S1 and S2 are making an angle of 90 degree, whereas this S1 surface is having, this is the electric field direction, this is the n cap. So, the angle between them is 0 degree, isn't it? So, this is n cap and the angle between them is 0 degree. So, when I want to find the net flux, so the total phi total will be equal to phi 1 plus phi 2 plus phi 3, and that will be equal to E into, I am writing S there. So, E into S1 cos 0 degree plus E into S2 cos 90 degree plus E into S3 cos 90 degree. What is cos 90? It is 0. But these two terms will get cancelled without any problem. So, what I will get, the total phi I will get as E into S1, cos 0 is 1. Now, what is the surface area? What is the curved surface area of a cylinder? It is 2 pi r L. So, I get the phi as 2 pi r L. Now, use the Gauss law. As per Gauss law, we know phi is equal to q by epsilon naught. So, phi I know it is E is equal to, if I write this as equation 1, I will write from 1 E is equal to phi is 2 pi r L. E 2 pi r L is equal to, instead of q I can write from here q is equal to lambda into L. I will substitute here. So, I will write lambda L by epsilon naught. So, from here L gets cancelled and I get the expression of electric field as 1 by 2 pi epsilon naught r. Lambda is there, sorry, lambda by 2 pi epsilon naught r. So, electric field due to an infinitely long charged wire will be lambda by 2 pi epsilon naught r. Now, let us see the next application of Gauss law, which is the finding of electric field due to uniformly charged infinite plane sheet. So, I am taking an infinitely plane sheet like this. Let it have charge. I can take plus or minus. The difference is if I take plus charge, then it will have outward electric field. If I take negative charge, it will have inward electric field. So, I want to find at any point, let the point be somewhere here, and I want to find what is the electric field at this point, which is at a distance of, from the center, from the plane, it is at a distance of r from the sheet. Now, again, to find the electric field, I want to draw the Gaussian surface. Gaussian surface, I am choosing it to be a cylindrical Gaussian surface, such a way that the Gaussian surface passes symmetrically over it. So, if I am drawing it here, it should pass something like this, symmetrically. Or symmetrically in the sense, why I am using the word symmetrically? Whatever r I have taken here, same r should be taken here, and obviously this area and obviously this area also will be same. The area is passing through the sheet because it is a cylinder. So, now I have taken a cylindrical Gaussian surface and I want to find what is the electric field at this point or created by this charged sheet. What I will do, first of all, see the normal vector to the area. Here 3 areas are there, S1, S2, S3, similar to the previous question. So, normal vectors, if you see here, for this curved surface area, this is a normal vector, for this is a normal vector, and for S3 this is a normal vector. Now, electric field, you see, electric field is not in this direction, only in this direction and this direction, isn't it? So, the net electric flux phi total is equal to what? Phi 1 plus phi 2 plus phi 3. So, E into S1 into cos 90 degree. Here E is in this direction and area in this direction, plus E into S2 into cos 0 degree plus E into S3 cos 0 degree. Now, cos 90 is 0, so first term gets cancelled and these two terms S2, S3 are same. So, I can write E S plus E S, which makes the total phi as 2 ES, right, 2 ES. This is the value of total phi. Now, since here the charge is distributed on the surface, I can take the help of surface charge density. So, surface charge density sigma is equal to Q by A, right, and using Gauss law, I can write phi is equal to Q by epsilon naught. So, phi value you can take from here. So, from equation 1, I can write 2 ES is equal to, see here the area is S. So, instead of A I can write S here. So, from here I can write Q is equal to sigma into S. So, Q is equal to sigma into S by epsilon naught. SS gets cancelled and I get electric field as sigma by 2 epsilon naught. So, what I came to know, that electric field due to a infinite plane sheet and which is uniformly charged is sigma by 2 epsilon naught. if you see very carefully, you will find that there is nowhere R value coming. So this electric field is independent upon how much distance you are going. Whether you are at this point or at very far point, this value will not change. It completely depends upon what is the surface charge density and not at all on the distance, how much far you are from the sheet, right. This is the value of electric field due to a uniformly charged infinite plane sheet. Usually from this part, the questions are frequently asked like this, where they will give you two plane charged sheets, right. So suppose both are positively charged and having different charge density sigma 1 and sigma 2, and both are positively charged. I mean to say like charge, both can be even negative. So both are positively charged plates, and they are asking you to find what is electric field at various points. They may ask you to say what is electric field here or here or here. Let me take the point as point number 1, point number 2 and point number 3. So we are going to find what is the net electric field at the first point or at the second point, at the third point. In order to find that, see, there are a lot of electric fields will be coming here, because sigma 1 will produce electric field like this, E1, E1. Sigma 2 will produce E2, E2, right. So how positive will spread? It will spread in the radially outward direction. Now, if I am finding at this point 1, right. So since there are different directions of electric field, I will take one direction as positive as a convention. So let me take from left to right. So I am taking left to right, that is R cap, from left to right as positive, right. So whichever direction will be against this will be taken as negative. That is the only reason why I have taken this R cap, to make sure I don't take wrong direction of electric field. So someone wants to take from right to left as positive, they can take, there is no wrong in that. So I am taking left to right field as positive direction. So all the directions in the opposite direction will be negative. So if we see at first point, so I am finding E at the point 1. So the electric field due to the sigma 1 will be in this direction and sigma 2 will be in this direction, E2, isn't it? So I will write E at 1 will be equal to E1 plus E2. Just now I have told electric field due to an infinite long plane sheet which is uniformly charged is equal to sigma by 2 epsilon naught. So it will be equal to sigma 1 by 2 epsilon naught. See, suppose I am finding the vector quantity, then sigma 1 by 2 epsilon naught, and direction of this is R cap, okay. And this thing for E2, it will be against, oh sorry, this is also in the against minus, so minus will come here. Why minus I have written here? Because see, direction of left to right is positive, but E1 is from right to left. Same way for E2 also it will be minus sigma 2 by 2 epsilon naught R cap. Plus should come here, fine. So what I get here, if I take R cap by 2 epsilon naught common, then I get minus also if I take common sigma 1 plus sigma 2. This is the value of electric field at first point. So electric field at first point will be 1 by 2 epsilon naught sigma 1 plus sigma 2 into R cap. Same way, if I want to find electric field at second point, then what will be that? Electric field at second point will be again E1 plus E2, and let us find that value. So E1 will be equal to, see, same positive direction, so it will be positive sigma 1 by 2 epsilon naught R cap, whereas E2 will be minus, so minus sigma 2 by 2 epsilon naught R cap. If I take common, so if I take R cap by 2 epsilon naught common, I will get sigma 1 minus sigma 2. This is the value of electric field at second point. And in the same way, if you find the electric field at the third point, E at the third point, see at the third point, E1 will be in this direction. So I can write E3 is E1 plus E2, and that will be equal to E1 will be sigma 1 by 2 epsilon naught. Since it is in the same direction left to right, it will be R cap plus sigma 2 by 2 epsilon naught, same R, both will be positive. So what will be the net electric field at third point? That will be equal to, if I take common R cap by 2 epsilon naught, it will be sigma 1 plus sigma 2. See, it is very, very simple, but understand the concept. This made it very easy for me to find all the values. If R cap I would have not taken that, I would have confused where minus, where plus will come. So These are the values of electric field at first, second and third point. Now suppose instead of two positive charged infinite plane sheet, if they take one positive and one negative and let it have same surface charge density but plus and minus. This is plus and this is minus, but density is same. Now see the direction of electric field. Again I will take from left to right as positive. Okay, direction of electric field will be outwards for this. Am I right? Here also outwards. For this thing, it will be inwards and inwards like this, isn't it? So this is the first plate. I write it as E1, E1. This is the first plate and this is the second plate. And sorry, I should write like this. It will be easy for me. First plate and second plate. So and this is E2 and this is E2. So E2 for here will come like this, and E1 for there will go in this direction. E1. Now let us try to find out what are the electric fields at this point and this point, that is first point, second point and the third point. So what is electric field at first point? Say in the same way, it will be equal to E1 plus E2. Let us put the values. It will be coming as sigma by 2 epsilon naught. Opposite to this thing, it is minus, and again plus E2 the same direction. So plus itself, and what are the same value, sigma by 2 epsilon naught. Isn't it get cancelled? It will be 0. Same way, if I want to find E2 second point, that will be equal to E1 plus E2, and what are the values? Let us check that. So E1 and E2 both are in same direction, so it will be sigma by 2 epsilon naught. R cap I can write if I want to write here. R cap was there. R cap plus sigma by 2 epsilon naught R cap. So sigma by 2 will be sigma by epsilon naught R cap. This is the electric field at second point, that is sigma by epsilon naught. And what is electric field at third point? Electric field at third point will be equal to again E1 plus E2. So the directions, that will be equal to E1 is in same direction of R cap, E2 is in opposite direction. So it will be sigma by 2 epsilon naught R cap minus sigma by 2 epsilon naught R cap. Both gets cancelled, becomes 0. So what we found, electric field here is 0 and here is 0. Inside I have a value of electric field sigma by epsilon naught. This kind of plates we are using to create a uniform electric field, right? Let us see the next application of Gauss law, which is finding electric field due to uniformly charged thin spherical shell. So if there is a thin spherical shell and I want to find what is the electric field due to this, I can find by the application of Gauss law. So if it is a uniformly charged thin spherical shell, so this spherical shell is uniformly charged. I said to you, whenever you are charging uniformly, you can expect that there is a charge present throughout the shell. So you can just imagine that there is a ball, football kind of thing in your hand, and throughout the football you have charges. It can be positive, negative. Once again I am saying, if it is positive charge, it will be radially outwards. If it is negative charge, radially inwards. So I want to find electric field at various points. I can find the electric field at this point, at the surface or inside the shell. So if I take the point to be outside, let the radius of the shell be r, and let the radius of this thing be capital R. So I want to find what is the electric field at the outside. So wherever you want to find electric field, by that point I can draw a Gaussian surface. So I have drawn a Gaussian surface, which is a spherical Gaussian surface having concentric circle with this, and now I am going to find what is the net electric field due to this charged spherical shell. So what I will do, see at this point the electric field direction will be outwards, and at this point even the area vector will be in the same direction. So I can say that total flux, net flux phi will be equal to E A cos 0, isn't it? This I am taking the case 1, and case 1 is for the point outside. So point is outside. So now phi is E A cos 0. So phi will be equal to E into what is the area, surface area of the sphere? It is 4 pi r square, isn't it? Now using Gauss law, we know that phi is equal to q by epsilon naught. So phi, instead of phi I can write E into 4 pi r square, that is equal to q by epsilon naught. So E comes to be, if I rearrange, 1 by 4 pi epsilon naught Q by R square. Now can you recall the formula of electric field? It is same, right? K into Q by R square, right? Now what I will do, I will try to find the electric field for case 2, and case 2 will be point on the surface. Point is on the surface of the sphere. So if this point comes here, see, this is the shell and the point is also on the shell. So what will happen? Everything remains same. Instead of capital R, it becomes smaller, because capital R becomes equal to small r, isn't it? So Gaussian surface is drawn at this shell itself. So I will get the final answer E as, this was E outside, right? Now I am writing E on the surface. So E on the surface will be equal to 1 by 4 pi epsilon naught Q by small r square. Also, I know that by the formula of surface charge density, sigma is equal to Q by A. So here area is 4 pi r square. So I can substitute Q from here. So Q will be equal to sigma into 4 pi r square. If I substitute here, I will get E at surface will be equal to 1 by 4 pi epsilon naught into Q is sigma into 4 pi r square divided by r square. These two gets cancelled, 4 pi gets cancelled, and I get the value of E at surface as sigma by epsilon naught. So if E is outside, it is 1 by 4 pi epsilon naught Q by r square. If E is at a surface, I get sigma by epsilon naught. What if the P is inside? This is the shell, okay, uniformly charged spherical shell, and I am taking the P point inside the shell. So if I take the point P inside the shell, if I draw a Gaussian surface here, am I enclosing any charge? No, because charge is outside. Since charge, this is the case 3. Case 3 is inside, point is inside. Point is inside. So since no charge enclosed, what will be the phi? 0, because phi is 1 by epsilon times net charge enclosed. Net charge enclosed is 0, phi is 0, phi is 0, electric field is 0. This concept is also used in electrostatic shielding, remember that. So we understood that electric field inside a uniformly charged thin spherical shell is 0. So what I got to know, if the point is outside, it is 1 by 4 pi epsilon naught Q by r square. When it comes on the surface, it is sigma epsilon naught, or you can write 1 by 4 epsilon naught Q by that r of the radius of the shell square. And if it is inside, it is 0. So if I draw it in a graphical way, if I represent it by a graphical method, so until the point is from the center to this shell, it is 0. There is no value of electric. So I am drawing the electric field here, and this is the R values. Okay. So until the R reaches the what R I am drawing, capital R I am drawing, until the capital R reaches the small r value. So this is small r. Small r is the radius of the shell. Radius of the spherical shell. So until that point, the electric field is also 0. At that value R, the electric field is maximum at this point. And what is this value? This value also you can write, that is sigma by epsilon naught, or you can even write 1 by 4 pi epsilon naught Q by r square. And as you increase, it starts to reduce. So electric field, we know the formula is 1 by 4 pi epsilon naught into Q by r square. So I can write electric field varies inversely proportional to r square. From here we came to know that, and this is how the graph is. This graph is very important for the competitive examination. So in today's class we saw that application of Gauss law. So what we learned? We learned the first application was finding the electric field due to an infinitely long charged wire, and we found the value of electric field to be lambda by 2 pi epsilon naught r. Then we found the value of electric field due to an infinite plane sheet which is uniformly charged, and we found the electric field value to be sigma by 2 epsilon naught. Using that case, we made two subcases where we found the electric field for two sheets, both were positively charged, and one was positive and one was negative. Later we found the electric field due to a thin spherical shell, at the outside point, on the surface and inside. We found it to be, if the point was outside, it was k into q by that point r square, and when it was on the surface, k into q by radius of the sphere square, and when it was inside, electric field was 0. With this, we come to the end of this unit itself. So now in my next video, I will be just giving a summary of the whole chapter, and I will try to solve all the NCERT questions also. Please be updated. Thank you.